Thank you very much, everyone, in both in person and online, for joining us today. Today we have a very good friend of mine and a rising star in uncertainty quantification, machine learning, and conformal prediction statistics, Yusuf Saleh from LMU in Munich. Today he's going to talk to us about a paper that just got uploaded on the archive. So very fresh piece of science. So, Yusuf, without further ado, the floor is yours.
Thank you, Michele, for the very nice introduction. I have to stand here because I have to click my way through it. As Michele mentioned, this talk will be about conformal prediction and in particular about online conformal prediction and in the intersection of selective inference. Hence, there is something going on. We have the online thing, the selective inference perspective, and conformal prediction. This talk, my major goal is that when you leave this room, that you have a clear idea of what we have done. And if you're interested in all the details, the paper is on archive. I will give you a link to that. You can check it, and I will be here till Friday. Please feel free to reach out. We can have any discussions around conformal prediction and uncertainty quantification. Before I start, let me maybe give you also some background information to my chair and to OR and my research. As Michele, is everything working?
Yeah, it's okay. Just good.
Okay. As Michele already mentioned, I'm from the LMU Munich and working at the AI ML chair there, and we have many topics going on, explainable AI, but the most, I would say, dominant one these days is about uncertainty quantification, and we all know how important uncertainty quantification is in machine learning. And most of my PhD work so far was on these notions of aleatoric and epistemic uncertainty in machine learning. First of all, how can we represent different types of uncertainties, and consequently, how can we actually quantify them? Today's talk will be a little different. I will jump straight into it. Before starting, this is a joint work with Aditya Ramdas from the CMU, and it was done basically during my time there. And huge credits goes to Aditya for a wonderful supervision and mentorship. Okay, but let me get straight into it. The problem setup. We have data arriving in a sequential and delayed manner, and time zero, we see a feature x0. For simplicity, we don't make any assumptions about the feature space, but just assume it's R or RD. Time 1, we see the new feature x1, and now the old label y0 gets revealed. You might imagine all y's are again maybe real valued or in a classification setting discrete. Till time t, at time t, we see the feature xt and the old or the label from time t minus 1, yt minus 1 gets revealed. Now, one question that we might be interested in is we want to do a prediction for our unknown yt. We don't have any yt here. We want to do a prediction. This would be in the realm of usual predictive inference. If we want to do it distribution free, we can do some conformal prediction. I will speak about conformal prediction in 1 second, but in this work we have, let me call it another layer of complexity, or like a selective decision-making layer. As you see in red, we have also an online selection mechanism going on. To give you a motivation, maybe in drug discovery or something like that, you don't want to always report a prediction region or prediction. Let's speak in this talk about prediction intervals. You don't want to report always a prediction interval because you're saying, you know, out of cost perspectives, computation perspective, you're just saying for now, I only want to report or construct a prediction interval if my online selection rule is met. This might be, for example, a very simple example, if my current feature is above 5, or let's say a constant C or below. And this is what these S are about. We call them, I will introduce them formally in a second. We call them selection rules, online selection rules, and hence the goal is we want to construct prediction intervals for the unseen YT if or time point xt is selected. Hence, ft of xt is 1. Let me be a little more formal about this. What we have here, I spoke about this very quickly. We have this ft mapping from x to 0, 1, an online selection rule. 1 indicating selection, 0 indicating not selected. Hence, if it's ft is 0, we're not interested at all in constructing a prediction interval. And correspondingly, this non-calligraphic ft is the so-called selection indicator. On the one hand side, we have the calligraphic one, which is the mapping. And on the other hand side, the instantiated one, which is the selection indicator. Now we define the filtration calligraphic YT minus 1, which is just a sigma algebra generated by all path decisions. Hence, at time point 0, we make a decision. Report, not report. At 1, we make a decision. Report, not report. Till t minus 1. And we say this ft minus 1 is contains just the information about the path decisions I made. And this is the only sigma algebra I will care about, or in general, the filtration generated in this way. Formally, we will be concerned about selection rules, which we call decision-driven. And these are just rules. These mappings are ft minus 1 measurable. What does this mean? This means that my selection rule only depends on past selection decisions. That is, in a sense, a restricted, but nevertheless, rich class of online selection rules. In this work, we consider selection rules, decision-driven selection rules, hence they are ft minus 1 measured. And as a simple, as a very simple example, let's say our feature space is just R, and the following selection rule is clearly decision-driven because it only depends on some constants, tau 0 and tau 1, and on my past my past selection decisions as 0 to st minus 1. So now previous slide in the problem formulation, I told you that okay, somehow our goal is to construct prediction intervals or make predictions for the unseen YT. And you might know that nowadays, in the past couple of years, even though conformal prediction dates back to the end of the 90s, work from Vogt, Gammermann, and Schaefer, conformal prediction somehow got a lot of attention as an uncertainty quantification tool. And today I'm going to, for those of you who are not familiar with this, give a very high-level intuition about the split conformal variant of conformal prediction. What happens is, let's have a look at our cloud. This is my data cloud, all the data that I have, and we do a random split. A D1, the blue part of the cloud, and a D2. D1 is called training data. We train some model on this and get a predictor at mu. And on D2, this is the part where the so-called calibration happens, and therefore we also call D2 calibration data. One major ingredient in conformal prediction are the so-called conformity or non-conformity scores. For example, absolute values, and they're just telling me how conforming or non-conforming a point is. What is happening now is we just define on the calibration data, or we compute non-conformity scores on the calibration data, D2, and just look at this Q hat 1 minus alpha R, which is just the 1 minus alpha empirical quantile. And we just compute my non-conformity scores, look at the 1 minus alpha empirical quantile, and call it, in this case, hat Q1 minus alpha. Then, how do we get our prediction intervals, or if the y's are discrete prediction sets? We just look or consider all y's and y to be an element, or to be contained in this prediction interval, where the corresponding non-conformity score is smaller or equal to this quantile. And those which, in a sense, somehow conform with this data. The interesting, or the thing that people appreciate in conformal prediction are the so-called finite sample marginal validity guarantees. This is what is in the box. Hence, with high probability, with a user-defined alpha, we know that the unseen yn plus 1 in this setting, in this non-online setting, is contained in this prediction interval with probability 1 minus alpha. That sounds promising. I mean, at least we have some statistical guarantees. And just one quick remark, because people tend to confuse this type of guarantees with conditional ones. We are not speaking about conditional guarantees. Hence, we are not conditioning on a specific x. Hence, we don't have condition like given x, big X being small x. We're speaking about marginal guarantees. This probability is taken over the unseen test datum and the calibration data. Hence can be seen as, if you want to take the expectation of the indicator as an expectation over the calibration and the testing. So we're still stuck with the problem setup, but as I said, the goal and what we did is clear, then I'm happy. In this work, we assume that, yeah, sure, go ahead.
Can we think of this this marginal guarantee as our rule of expectations of indicators, like the expectation with respect to the x's, of the expectation with respect to the y, of one of the indicator that y is in that given x?
That's a good question. I mean, how do you want to formulate the tower property in this
like
case?
E of x, E of 1 of y in C hat 10 plus 1 x n plus 1.
That's a good question. I mean, I'm not so sure about this type of formulation.
But it's fine. It's just
yeah. No, but
something
we can speak about this. Yeah.
Thank you.
No worries. Yeah, as I was saying, we assume in this work that we have access to some amount of fixed data, or let's call it offline data, and we also do this assumptions that my online selection rules that we introduced earlier are independent of the fixed data. The selection is done, from 0 onwards, but for the sake of that we have at least access to some data, and we will relax this assumption, but still that we assume that we have access to some offline data. Looking at this axis here, again, what is happening from 0 onwards, we are observing online data, and now once we have that STXT is 1, hence a selection is made or indicated, we want to construct a prediction interval for this unseen YT such that we have, again, these type of guarantees that we spoke before in conformal prediction. Hence, what we want to have, that the probability of YT being in this prediction interval, given that I made a selection, is larger or equal 1 minus alpha. In a sense, this resembles exactly what we have in the usual conformal prediction setting. But here we have the selection mechanism involved. We are saying, okay, we want to have this guarantee conditional on when I make a selection, because I'm reporting only prediction intervals once I'm making a prediction. And in these cases, I want to make sure that my YT is in this prediction interval with high probability. You might maybe already guess that there might be some problems. Well, let's maybe talk about the most straightforward thing. Before, when I introduced quickly split conformal prediction, I told you that we need training data, D1. You remember this cloud, the blue part. And we could now say, okay, let's train our model. Let's assume we have a pre-trained model, head mu, and this is trained on this D1, this online data, this D1. And now, what do we use as calibration data? Like a very straightforward thing. You might say, yeah, okay, but why are you not using the rest of the data? All of the data, hence in this orange box, as my calibration data till t-1. I guess maybe it's already clear that there might be some problems, because something that I, on purpose or not on purpose, left out is, if we go back here, what are actually the assumptions that we have in conformal prediction? It is distribution free, hence for every distribution of the xy's, we will have these guarantees, but there is this mild assumption of exchangeability. In the split conformal variant, we assume that the test data, hence here in this case in the online setting, at time point t, my xt, yt, let's call this zt, is exchangeable also with the calibration data. Hence, this calibration data plus test data are exchangeable. And this is no more the case, or might not, this exchangeability might be violated once I have a selection procedure involved. Because let's maybe motivate just this part. Let's talk about why this can't work just using my calibration data as it is. For example, saying, let's use the fixed data and all online data until t-1 as my calibration. But what happens here? We have a asymmetric dependence. Time, this red time t, is selected, on the basis of a rule. And it might be, for example, FT is telling me or telling you, just select or report prediction intervals for those features, xt, let's speak of a single feature, xt, where it is above 1000. Okay, then I'm reporting only for those guys, but I'm including everything that I saw in the history, not just above 1000, but any values that I have seen. And takeaway is I'm creating an asymmetric dependency, and what this leads to the fact that exchangeability is often violated. Coming to also to the motivation of our work, we might somehow think of strategically selecting or picking calibration data. That is, we know blindly putting calibration data in the calibration pot is maybe not the best strategy. But the assumption that we also make is that this is a strong assumption, but from a scientific perspective, very important, that we say my online data and my fixed data are already exchangeable. I'm breaking exchangeability by my selection mechanism. Now, can I somehow restore exchangeability that I had by suitably picking my calibration data? And interestingly, there was, and here at this point, I have to say, in this realm, there's probably, with our paper right now, probably 3 papers on this question in the online setting. There are many more in the selective setting, in the offline setting, but the online setting has more problems attached, because we have like the temporal dependency issues. We talked about these decision-driven rules, which depend only on the past decisions. And Let me formally introduce what is happening. We have here this calligraphic IT is just called calibration selection protocol. And if you see there are too many formulas, just imagine it that way. It is just telling me which data point in my potential pot, and my potential data somehow pot is everything that I've seen in online fashion from 0 to t-1 and my fixed data. And this calibration selection protocol is just telling me which data to include in my calibration data. Hence, exactly this part, and JT, to give you some more notation, is just are the indices of the fixed data. Let's call it -n to -1. And from some online data from 0 to t-1. And this guy is just telling me, okay, if it's 1, include the jade candidate data point into my calibration dataset. But there might be different strategies. We saw already one very straightforward naive strategy, put everything there. And these strategies are, you can see there's a calligraphic K, or let me call it kappa. Those kappa T's are called calibration selection strategies. As I said, just telling me how to select calibration data. For example, here on the bottom half of the page, the data points in purple, and -n, k, and t-1. For this, my calibration selection strategy indicated select or put this point into my calibration data, and for the other ones, it's just 0. And in this simple case, my calibration data would consist of -n, k, and t-1, the indices. Also, to give you some maybe historic background to this work, there was a recent paper, I will also show you the references at the end, that already saw these limitations or these problems with this, asymmetric dependency, exchangeability, and proposed a strategy which they claim that solves the problem. In this paper, we refute it, and we propose strategies that actually are doing what we want. But coming again to the point of departure again, the one that we discussed before, we call it the full strategy. Just put everything in my calibration data. And -n to t-1 is purple. Purple indicates putting into the calibration data. The second strategy, which might already sound somehow good, but is not, is the so-called selection full strategy. To use abbreviations, let's call it S-full. Just selects calibration data according to the selection rule given at time t. In formulas, my calibration strategy is just ft xj for all j, or all potential candidates, calibration candidates. What does this mean? This means at time t, I have a selection rule, ft. And we had this very simple example of, I don't know, I'm selecting if x is above 1000. Now, I'm not saying I'm only reporting prediction intervals for this when the selection rule is met, but I'm also including calibration data into this calibration pot once the potential candidate feature is above 1000, for example. This sounds somehow good, but in the online setting, we have some problems because we are in a temporal setting, and this rule will still, in many cases, break exchangeability. To motivate you for this, what does exchangeability mean? Exchangeability mathematically means, okay, if for any permutations of data, in the sense my data is the test data and calibration data, if I permute them, the joint law will stay the same. Now, if I permute here also in this setting, for example, the purple data, hence my t-1, 0, and -1, -n, it might happen I cannot guarantee that I select my time point, do a selection at time point t, because I have a decision-driven selection rule. It depends on the past data. And this is obviously a problem, and there are many more problems to that, but to give you a motivation. The second thing, which might be interesting, it's a very simple thing. It's called the selection fixed strategy, S-fix, which basically selects calibration data solely from the fixed data. And you might imagine that this is not very problematic. A problem might be that you end up, if you have a very large time horizon, with very few calibration data. But what does this rule do? I mean, here we are just selecting with the rule given at time t from this offline data, this fixed data. And as a recall for you, we assumed that the selection rules, these online selection rules, are independent of my fixed data. Hence, they're, in a sense, you're not causing any problem. But as I already motivated, one of the problems might be that I end up with, a negligible amount of data because I have so many online data and not that many offline data, and I'm only selecting on the offline data. Let's come maybe to the quite interesting part. Bao et al. In a 2024 paper, they published it or put this on arXiv in 2024, recently introduced so-called adaptive calibration selection strategy. They saw, okay, like naive things like selection fixed or selection full are not really working. We have these violations of exchangeability, and they arrive to the following solution. They just say, okay, the adaptive strategy is telling me do select with the rule given at time t on the fixed data, because you don't have any problems with this because of the independence assumption. And on the online part of the data, do the selection as follows. We have here the selection in the online part of the data, and hence telling us how to select data from my online data. This is true if the whole thing here is 1. That means if I have ftxj is 1, I would select the jade candidate with respect to the rule at time t. And I'm also guaranteeing that this sjxj is equal to sjxt. Mathematically, there is a lot going on here because of how they arrive to this solution, because one thing they want to make sure is that once you permute the data, that in a sense your selection rules stay the same. We have these decision-driven selection rules, and as I said before, if you would somehow permute my data, you might change the sequence of selection rules. And they somehow try to make things more symmetric. And they claim that this type of or degree of symmetry is somehow enough. But we will see in a second it's not. Now, what do we actually do? We propose novel calibration selection strategies. The first one, or a family of, it's better to call them a family of calibration selection strategies. The first one is called the so-called exchangeability preserving strategy, and we named it that way because it's preserving the exchangeability of my data. And the rule is, in a sense, similar to the one of Bao et al. But what we have here is that we are saying, okay, only put my jade candidate into my calibration data if this whole guy here is 1, which means I would select with respect to the selection rule given at time t. And I have to guarantee that or I require the identical path selection decisions for both the candidate calibration point and the selected test datum. Hence, I know that this might sound on the first view a little, complicated, but the only thing is, I'm just saying I want to behave them in a fully symmetric way. And I want for all past selection decisions, the candidate calibration point and the selected test datum to behave symmetrically and mimicking in a sense of, in a way, restoring exchangeability. Okay, but what is obviously the problem? Since I'm requiring this identical behavior and this full symmetry, I will at the end up with few to none calibration data. In some cases, it's quite interesting that it works. There are reasons for that, but imagine you have a very huge time horizon. I don't know, high frequency trading or something like that. And now for, I don't know, millions of online data, you have to guarantee that all past selection decisions are the same as for the online, the test data. Obviously, you will end up with not that many calibration data. A second, or a variant of this one, we introduced is called the K-exchangeable preserving strategy, K-express, and this is very simple because instead of saying, okay, because here the product is over all online data, we're just saying, let's somehow do this express strategy that we had, but only for the last K points. And in a sense, I want to be less restrictive. I'm not asking identical path selection decisions for the candidate and the test datum, but I'm saying just for the last K ones. One maybe drawback is, okay, I can have, a total amount of K calibration points for sure. But on the other hand side, I have, or at least I can have some calibration points. And I'm speaking all the time about these calibration points, but as you've seen in the conformal prediction framework, it is very important because if I end up with, for example, 0 calibration points, what will happen is by design, my prediction intervals are of infinite width. And at least I want to guarantee some calibration points. Good. A final strategy is, before I move on to some theoretical and experimental results, also to stay in time, is called the expressed merge, or for short express M. And very simple one. It is just saying, let's apply the S-fixed strategy, to recall, just selecting from the offline data, fixed data, and also separately apply this restrictive one, the express. Now what happens is we have two procedures or two conformal predictions, one with S-fix, one done with express. What we do is we just merge the resulting prediction intervals and get a merge. And this is simply done, and all the theoretical guarantees we still have by just Bonferroni inequalities. And what happens is this mitigates somehow the restrictiveness of express by leveraging the more inclusive nature of S-fix. Our idea was, okay, if the other rules that we propose are in a sense restrictive, let's somehow try to be less restrictive and have something more applicable. Okay. Also, to somehow reflect on the title of my talk, Online Selective Conformal Prediction, let's go through these steps involved in online selective conformal prediction. I already motivated, hopefully, each of these points. The first one, we specify the selection rule ST, in this case, decision-driven one, and FT and FT minus one, before observing the current feature XT. Now we observe our feature XT, and if ST is 1, we decide to report a prediction interval for the yet unobserved YT. The third step, we specify the calibration strategy KT and observe or obtain the calibration indices calligraphic DT. Now we proceed as a motivated and split conformal way. We compute the nonconformity scores Ri, hence for this calibration indices that we obtained from my strategy, I compute the nonconformity scores of my choice, might be absolute residuals or something that I want. And finally, I construct prediction intervals in the same way as I had before. Hence, I include every y where the corresponding nonconformity score is smaller equal than my empirical 1 minus alpha content. That's it. And if we do it that way, we can look at some experiments. I was thinking that we have already some theoretical results, but yeah, they will come later. This first simulation is to somehow also give us some more evidence, empirical one, for the things that I motivated, such things that this full, S-full, or adaptive form are actually not working. Let us remind us what the goal was. We wanted to somehow have this guarantee, the selection conditional coverage. With high probability, my YT is in my constructed prediction interval conditional on that I made a selection. And what was the main ingredient, as it is usually in conformal prediction? Exchangeability. And to restore exchangeability, we went this whole way of calibration selection, calibration data selection. Now let's see this very simple simulation. We generate data of size n, and we have some n fix, small n fix, which is some offline or fixed data, and we have some online data and on. And in this very simple example, we fix the offline data to be 10 and the online data to be 20. Now what we do is we just generate a univariate feature, x. It's uniformly distributed between 0 and 2, and model the response in a linear way. And or y is given as mu x plus epsilon, where my mu x is just linear, and x beta. And we assume some heterogeneous noise, and my noise distribution follows Gaussian with variance x over 2. Also, we use this selection rule for all t bigger equals 0 that I motivated before, and the mapping, which maps x to the indicator of x smaller than tau 1 plus 1 over tau 0, and the sum of these SIs, clearly decision driven. And this is maybe not that important because we are free to choose anything we want, but we choose tau 0 to be 20, and somehow resembling the 20 online data there that we use, and tau 1 to be 1. What is the takeaway, or what are we, in a sense, checking? We're checking selection conditional coverage. These blue crosses, and the y-axis is our miscoverage, or alpha, that we set. And the goal is to be, in the ideal case, on or specified 0.4. And in this 1 minus alpha, this alpha would be 0.4. And also, if we are below, we have this guarantee of larger than 1 minus alpha. What is, in a sense, bad if we are, above? And we can see in this case for the S full and adaptive strategies, and just as a small remark, this is done over 10 or 100,000 repetitions, because this is a very synthetic, simple case, and this runs quickly through. And we see that empirically, we can somehow refute that these two strategies are not working. This full strategy is also not working, but in some cases it tends to work. And in the appendix, we also have some examples where S full is not working or full is not working. Let me maybe go quickly over the takeover of this experiment. In these boxes, we have in orange the percentage of infinite length prediction intervals. Clearly, for all these other rules, full, S-fix, S-full, other, 0%. Hence, all provided prediction intervals are of finite length. But as I was already saying, due to the restrictive nature of K-express, we see that for express, almost 14% of the reported prediction intervals are of infinite length, which might be a problem. If you're a practitioner and get in 14% of the cases infinite length prediction intervals, you might say, okay, this is maybe not very useful. But we will see that this is quite better with the merge one, 3.7%, and for the express one, 5.3%, and for the express one here, we just use the last 5 online data. First takeaway, the restrictive nature is clearly here of also the newly proposed rules. Plus, we see already the problems with these existing strategies. Looking at the middle boxes are the report or are the median prediction interval lengths, and we see like that with the having in mind that we're reporting the median, and we have here 14% infinite length prediction intervals. We have that express yields the shortest intervals, and express M and 5 express also perform comparatively nicely. Hence, at least for this express M and 5 express or K express in general, it seems like there might be also real like practical use cases. Like very informally stated, but one of the main theorems that we have in this paper is that online selective conformal inference with S-fix, express, express M, also K express, which is missing here, produces selection conditional prediction intervals, hence again fulfills this 1 minus alpha selection conditional guarantee for any t larger or equal to 0 whenever we have a positive probability of selecting. And as I said, the key is to show that the calibration data and the selected test data are exchanged. I'm not providing the proof here. Feel free to check it, or we can discuss offline. But this is really the key, because the rest follows by simple conformal prediction arguments. And to the best of our knowledge, this is actually the first algorithm that really satisfies this in the online regime. Let me go quickly over the smaller second part. I might skip 1-2 things. We talked about selection conditional coverage, which is obviously quite natural metric to assess somehow the errors that we made in or that we make in online selective conformal prediction. But another somehow important metric is the so-called false coverage statement rate, which is motivated from statistics itself, and super simple. It is just the expected ratio of number of reported prediction intervals failing to cover. And we're just looking, okay, how many prediction intervals did I actually report, which is here, the maximum of 1 and the sum. The sum is basically telling me how many did I report. And here we just are saying, okay, how many of those that I reported are actually not covering. And what we want to have in the ideal case is FCR control. And we again say, or the practitioner is telling me, hey, I'm giving you an alpha, let's say 0.5 or 0.5 or something like that. And I want to have my FCR controlled below this target level alpha. So very quickly again into this, we have here the FCR. simulations. I did not provide the precise simulation or how it is working because it's exactly the same as we had before in this very simple way. But in this case, we let our time horizon go to 200 and we have access to 50 offline data. What we have on the y-axis is the FCR, as we have seen before. And our target is this 0.4. Hence, we want to have FCR below or equal to our alpha, where our alpha is 0.4. What we see in this case is that, which is super interesting, that this newly proposed one, this adaptive one, is actually not controlling the false coverage statement rate, which is in a sense not good because the authors claim that this adaptive one provably does control FCR. While our methods, K-express, express M, and also this S-fix controls FCR, and here also by the choice of simulation and the selection rule, full and S-full seems to control it, but we can show theoretically also in other experiments that this is actually not the case. We have a similar takeaway here. If we look at the calibration data, y-axis denotes number of calibration data. On the x-axis, we have time, and we see full accumulates in an unrestricted way because we put everything in there. Calibration data, S-full in a similar way. Also, this adaptive one accumulates a lot of calibration data, which is good, but if we cannot theoretically show selection conditional coverage and FCR control, then it's more or less a heuristic, because then you're saying, I can't give you any guarantees, but it works somehow. And yeah, but it's not theoretically well grounded. While for the express M, express, and here in this case, 10 express, because we used the last 10 online data points for calibration purposes, we see a more restricted amount of calibration data that we can actually accumulate. Also for S6, since we said we have access to maximum of 50 calibration data points, it can get only to 50. Another thing that is somehow again confirming what I said earlier, here on the left plot, C, we have on the y-axis the percentage of infinite length prediction intervals. We see for express that over time, this fraction gets quite huge, 16%. But a positive message here is for express M, actually, we don't have any prediction intervals of infinite length. Seems to work good. Also for this K-express, we have under 2% prediction intervals of infinite length, which is maybe a negligible amount, because also in standard conformal prediction, it happens that we have prediction intervals of infinite length sometimes. Also, I would say this plot D is quite surprising because the intuition is somehow, okay, more calibration data, shorter prediction intervals, but we also have the selection bias in there. And here in this, I constructed this simulation of the synthetic experiment that way also to show that here, for example, this full strategy, which has the most calibration data, actually yields, even though the guarantees are anyway not satisfied, the largest prediction intervals because I have a selection bias. And we see here that also the ones that probably satisfy these guarantees are highlighted with a green tick. Also that express M and express are performing quite good. Okay, given a little the time constraint, let me just go over the proposition and skip the last part. We can show that online selective conformal inference with these calibration strategies, S-fix, express, express M, and K-express, also missing on the slide, guarantees that we can control FCR below our target level alpha. And oops, actually, again, this is, to the best of our knowledge, the first algorithm which can simultaneously control selection or can fulfill selection condition coverage and control FCR. I had also very quick part of other methods, but I guess I will just skip this, and we can speak of this offline version. Let me dive just into the conclusions before answering questions if you have some. Key takeaways. We evaluated existing calibration selection strategies and identified more or less fundamental errors in recent proposals. And we proposed novel calibration selection strategies on our own that provably preserve or restore exchangeability. And on top of that, we proved that these strategies guarantee selection conditional coverage. And as I said, to the best of our knowledge, this is the first one to do so. And also provided experimental validation, highlighting the trade-offs between valid methods and this restrictive nature, because we want to have selection conditional coverage, FCR control, but it should also be, in a sense, applicable. Yeah, but let me stop here maybe at this point and take some more questions.